Welcome back, everyone. So we're going to start with this slide today, and I really like this slide, aside from it being humorous, is that it does a good job of summarizing what we have talked about so far with regards to the two models of the atom that address where an electron resides in that atom. So in the first model, we talked about the Bohr model, which hopefully you didn't find boring. But in that Bohr model of the atom, electrons traveled around the nucleus in specific paths called orbits. These orbits, shown by this elliptical nature here, these orbits have particular paths, they have particular energies associated with them. So in the Bohr model of the atom, an electron travels on these paths called orbits. They can go from one orbit to another by absorbing or releasing energy, but those are the only places where an electron can be in the Bohr model. And the Bohr model works great for species that have just one electron, like hydrogen. But once you start adding more electrons to your atom, which is essentially all the other elements in the periodic table, then the Bohr model falls apart. It doesn't adequately explain where an electron is in an atom. And so we need to look at a different model, a different way of looking at the atom, and that's where the quantum mechanical model comes into play. So in the quantum mechanical model, we don't have orbits anymore, paths where an electron travels. We have these things that are called orbitals. These orbitals are particular regions of space where we can say that an electron is most likely located. Okay? So these orbitals is what we're going to be talking about them in more detail in this video, specifically what these orbitals are called, how do we get these numbers and letters associated with orbitals. And then in the following video, we're going to talk about how we can use our best friend in this class, the periodic table, to determine what orbitals are used for what electrons in an atom. So this slide is just sort of a summary of the quantum mechanical model, or the quantum mechanics that we have talked about so far with that second model. Two of the pros of the quantum mechanical model is that it takes into account the fact that an electron is a particle, it has mass, and it also interacts with and emits energy, like it did in the Bohr model. So essentially what the quantum mechanical model does is it uses a bunch of fancy math and physics and equations that you talk about more in Chem 1 and a lot more if you go on in chemistry and physical chemistry. It uses a bunch of fancy equations to find solutions for these orbitals that were shown on the previous slide. We are obviously not going to be doing any of that fancy math to determine equations for orbitals. What we will do in this class is use the solutions to these fancy equations, and the solutions to these fancy equations are called quantum numbers. Quantum numbers. There are two quantum numbers that we will talk about in this course. And what's great about these quantum numbers is that you don't have to memorize them, but you can use the periodic table to determine the quantum numbers for a particular electron in a particular atom. Okay? So that's what we're going to talk about in the next video. The rest of today's video, is going to talk about what is going to define what these two quantum numbers are. And when I say quantum numbers, I said that those were solutions to fancy equations we're not going to talk about. But I think it's helpful to think about these quantum numbers as akin to an address. either an email address or a snail mail address, but a way that chemists explain where an electron is in an atom. And so you can think about these quantum numbers as the address for an electron. Chemists call these quantum numbers, but sometimes they also call them electron configurations. And so in subsequent videos, we're going to use these quantum numbers to determine an electron's address or an electron configuration for a particular species. Okay? So in the quantum mechanical model that we talk about in intro, there are two parts to the quantum mechanical model, two parts to an electron's address. Okay. Those two parts include a number and a letter, and both of those specify the orbital. Think about the orbital as like the house of the electron, where the electron resides. Every address for a house has a house number and a street. You can think about this number and letter as like the address for that house or for that orbital. So the two parts are the number and the letter. The number is called the principal quantum number, and it is designated or symbolized by this letter N, and it specifies the shell of the orbital. So think of the shell as the street that your orbital is on, or the street that your house is on. This principal quantum number, or N, says something about the energy of the orbital. How much energy that house, how much energy that region of space has. And so similarly to orbits in the Bohr model, with the principal quantum number, we use these numbers starting from 1 and increasing. And as your N level increases, the higher amount of energy that is present in that orbital. So for example, an orbital that has a principal quantum number of 2 is going to have more energy than an orbital that has a principal quantum number of 3, and so on and so forth. So the first part of the electron configuration, or of an electron's address, is a number. It's called the principal quantum number, and it starts with number 1, goes up in subsequent jumps of 1. The higher your principal quantum number, the more energy that orbital has. So we have a number and we have a letter. The letter is the second part of the address of an electron. So the definition of this letter is that it indicates the subshell of the orbital, but I think it's more instructive to think about this letter as to say something about the shape of the orbital. Or specifically, if you want to still think about in terms of houses on a street, think about this letter as designating the shape of the house. Okay? Not every house has the same shape. Some houses are bigger and smaller than others. Similarly, some orbitals are bigger or smaller, have different shapes than others. So this letter, this part of the electron's address, this letter can have 4 possible values, or 4 possible choices. Those letters for the subshell are S, P, D, and F. Now, how they got, why scientists decided on those letters, you can kind of see here, is based upon the shape of the region of space, or the shape of the orbital, where an electron is for that atom. So for example, an orbital that is an S orbital, the region of space where that electron resides is spherical, hence S. Okay? So you can see as our orbitals progress from S to P to D to F, the shapes get much more complex and much larger. Okay? So obviously we're not going to be deriving these, but what you do need to know is that the letter portion of an electron's address, the letter is either S, P, D, or F. That letter corresponds to an orbital to a region of space that has a particular shape, be it spherical, dumbbell, cloverleaf, or very, very complex. Okay. So we have two parts to our electron's address. We have that principal quantum number, which says something about the energy of an orbital. And we have the letter, which says something about the shape of the subshell or the shape of the orbital that that electron resides in. Ooh, that was neat. So you may be thinking, okay, that's great. How do I use that information, or how do I get that information? How do I use the principal quantum number and this letter S, P, D, or F to say something about where an electron is in an atom? Well, what's great is that you can use your handy dandy periodic table to determine the electron configuration or the principal quantum number and letter for a particular electron in an atom. So in the next video, we're going to start with this slide, and we're going to talk about how you can use the periodic table to determine the electron configuration or the quantum numbers for an electron in an atom.